In our previous video, we tried to explain the rate of change. We explained that if you have a function dv dr and v is volume, r is radius, it means the rate of change of volume with respect to radius, similar to the a, the r. If a is area and r is radius, it means the rate of change of area with respect to radius. You can watch out the video for a better understanding. But what if we have a situation where the area is changing and the radius is changing at the same time? Can we compare the rate at which each of them change at the same time? Take for instance, if I drop a stone inside water, it will form a ripple. Let's say the ripple started small like this and expands to this point before it fades away. It's actually this small area that changed to this small circle that's changed to big circle. And looking at it carefully, both the area and the radius changes at a constant rate. Is it possible for us to compare the area, to compare the rate at which the area changes and the rate at which the radius changes? And that's what we are going to look at in this video. Please subscribe to this channel and don't forget to send us email at Science eLearning Academy if you have any question regarding to any video. Just send us email. We'll get back to you as soon as possible. Assuming y is a function of x and we want to know the rate at which y changes with respect to time, then we can say that dy dt is equal to dy dx multiplied by dx dt. This formula means that for you to know the rate at which y changes with respect to time, you will first of all know the rate at which y changes with x, since it's a function of x, and you will know the rate at which the x changes with respect to time. And this is the formula we will apply in solving this, comparing the rate of change, because we can now compare the rate at which y changes with time and that of x changes with time. Consider this example. The question said, if the volume of a hemisphere is increasing at a steady rate of 18 pi meter cube per second, at what rate does its radius change when it is 6 meters? So let's write down the parameters. The rate at which the volume is increasing steadily, that is dv dr, dv dt is equal to 18 pi meter cube per second. Then we are asked to find the rate at which the radius change. So we're asked to find the r dt, but we're given that the radius itself is r is 6 meters. So, and we know that v is a function of radius. Applying the formula we stated before, you can say that dv dt is equal to dv dr multiplied by dr dt. And we were given dv dt and we are asked to find dr dt. So if we can find dv dr, then we are good to go. So but for us to find dv dr, we already know that the volume of a sphere is equal to 4 divided by 3 pi r cubed. Therefore, for a hemisphere is half of a sphere. V of hemisphere will be equal to half multiplied by 4 divided by 3 pi r cubed, and this is equal to 2 divided by 3 pi r cubed. Therefore, dv dr is equal to 3 multiplied by 2 divided by 3 pi r square, and this is equal to 2 pi r square. But we were given that r is 6 meters. If we substitute r to be 6 meters in this, then we'll be having that the VDR will be equal to 2 pi 6 squared. And this will be equal to the VDR is equal to 2 pi multiplied by 36, and this is equal to 72 pi. We already know that this dv dt is 18 meter cube per second. The unit of this is in meter because volume is in meter cube and radius is in meter square. Radius is in meter, so this should be meter square rather. Therefore, if we can substitute this 72 pi meter square in this expression, then we can find the r dt. So we have that this is 18, dv dt is 18, is equal to 18 pi. Then dv dr is 72 pi multiplied by dr dt. So making dr dt the subject formula, we have that this is 18 pi divided by 72 pi. And we can decide to simplify this. We'll be having this should be 1 divided by 4 in meter per second. This is the final answer. It can as well be written as 0.25. 1 divided by 4 is 0.25 meter per second. This is as well the final answer, either this or this. Consider this question too. The question says the radius of an ink drop on a blotting paper expand at the rate of this. We already have that the r dt is equal to 0.02 cm per second. And we are asked to find the rate at which the volume changes, the area changes, which is the A, the T. But we're given that R is 5 cm. Therefore, we have that A is a function of R. And from our formula, we can say that the A dt is equal to the A dr multiplied by the R dt. And if you drop an ink on a paper, it will form a circle. And we are looking at the area of a circle in this case. So the area of a circle is pi r squared, and we can say that the ADR is equal to 2 pi r, and we already have the r to be 5 centimeters, and this is equal to 2 pi multiplied by 5, and this is equal to 10 pi in meters. Area is meter square and radius is in meter, and have 10 pi meters. Therefore, if we decide to find the A dt, and this is equal to, if we substitute this and this, don't mind me, this is centimeters because all the units are given in centimeters. The A dt is equal to the ADR. The ADR is 10 pi, and the R dt is 0.02, and this will be equal to 0.2 pi centimeter square per second. This is the final answer.